Have you ever wondered what time truly is? Is it mere seconds ticking away, or something far more profound? Time is a concept that has puzzled philosophers and scientists for centuries. Is it the relentless march of the clock's hands, or is it a dimension much like those of space? According to Albert Einstein, time is not an absolute entity, but a relative one. His theory of relativity suggests that time can speed up or slow down, depending on the speed at which you are moving and the gravitational field you are in. This idea of time being flexible rather than fixed was a revolutionary shift in our understanding of the universe. Now, picture the universe as a four-dimensional fabric known as the space-time continuum. Three of these dimensions represent space: the up and down, left and right, and forward and backward. The fourth dimension is time, which is intertwined with the other three. This means that we cannot consider space and time as separate entities, but rather as a single unified field. But what about the direction of time? Why does it always seem to move forward, never backward? This brings us to the concept of the arrow of time, which is deeply connected to the second law of thermodynamics. This law states that the total entropy, or disorder, in an isolated system will always increase over time. This gives time a direction, from the past, through the present, and into the future. Therefore, time is not just the ticking of the clock, but a fundamental aspect of our universe, bound up with space in the four-dimensional fabric of the universe, and always moving forward due to the increase in entropy. It's a complex, multifaceted concept that is still not fully understood even by the brightest minds in physics. So, time, as we understand it, is a complex, multifaceted concept that is deeply intertwined with the very fabric of our universe. If time is a dimension, much like the three spatial dimensions we experience, could we potentially travel through it, just like we do through space? To delve into this, let's start with how time travel has been depicted in science fiction. From H.G. Wells's The Time Machine to the Back to the Future trilogy, time travel has been a fascinating concept that has stirred the imagination of writers and filmmakers alike. These depictions often involve a physical machine or device and the ability to move backward or forward through time at will. But what does science have to say about it? Can we pack our bags for a trip to the Jurassic era, or maybe fast forward to a utopian future? Well, it's not that straightforward. The idea of time travel is not completely out of the realm of scientific possibility, but it comes with a hefty dose of complexity. Albert Einstein's theory of relativity, for instance, entertains the possibility of time dilation. This concept suggests that time can slow down or speed up, depending on how fast one is moving relative to something else. So, in a sense, astronauts aboard the International Space Station are time travelers, aging slightly slower than US Earthlings due to their high orbital speed. Then there's the concept of wormholes, a theoretical passage through space-time that could create shortcuts for long journeys across the universe. If these wormholes could be found or created, and if they are stable enough, they could theoretically allow for time travel. But here's the catch. Even though these ideas are backed by robust mathematical equations, we currently lack the technological means to test them experimentally. We are still grappling with the challenges of creating or finding a stable wormhole, not to mention the energy it would require to keep it open. While time travel remains a fascinating concept, it's important to remember that it's largely theoretical at this point, with no definitive evidence or method known to mankind. If time travel were possible, wouldn't it lead to bizarre situations and paradoxes? Let's delve into some of the most famous thought experiments that illustrate these paradoxes. We'll start with the grandfather paradox. Imagine for a moment that you had the ability to travel back in time. You meet your young, spry grandfather before he had any children, and, in a twist of fate, you accidentally cause his demise. If your grandfather never had children, your parent would not exist, and consequently, neither would you. But if you don't exist, who traveled back in time to cause your grandfather's untimely end? This paradox puts into question the very nature of causality and the order of events, presenting a scenario where the effect precedes the cause. Next up is the bootstrap paradox, named after the impossible task of lifting oneself by one's bootstraps. Let's say you're a musician and you travel back in time with a song you wrote. You meet a young music prodigy who learns this song from you. As time progresses, this prodigy becomes famous for composing this song, which is the same piece you learned and took back in time. The question is, who originally composed the song? It seems to exist without an origin, stuck in a cyclical loop of time. These paradoxes aren't just head-scratchers for scientists and philosophers, they also raise ethical and moral implications. If we could change the past, should we? Would it be ethical to rewrite history, to erase our mistakes, or alter the course of events? And who gets to decide what changes are made? The allure of time travel is undeniable. The possibility of revisiting the past or sneaking a peek into the future has a certain romantic appeal, but it's not without its complications. While the concept of time travel is enthralling, it opens up a Pandora's box of paradoxes and dilemmas that challenge our understanding of reality.